Good morning, students. The next lesson is electromagnetic induction. See, this is very important lesson and very easy lesson. For student point of view, it is so easy. In this lesson, each and every concept you can learn easily because in this topic the number of questions are very less, the concepts are easy, and damn sure questions you can get from this chapter. So that is the reason I am requesting you, all the students, you have to focus this topic and you can finish this topic within 1 hour or 2 hours. It maximum takes 1 hour or 2 hours for learning point of view. Okay. What we are going to learn in this topic? First, what is the meaning of electromagnetic induction? Then later we will learn magnetic flux, different cases of magnetic flux, and Faraday's laws. Based on the Faraday's laws, coil magnet, again coil, experiments we learn. The later we see the Faraday's laws of electromagnetic induction, Lenz law, and proof of Lenz law, motional EMF, eddy currents, applications of eddy currents, and later lastly we move to AC generator. So this is the total topic about this electromagnetic induction. See students, first, what is the meaning of electromagnetic induction? Induced EMF is produced in a circuit due to change in magnetic flux or change in magnetic field. Because of change in magnetic field or change in magnetic flux, induced EMF is produced in the circuit is called electromagnetic induction. Once again, I am repeating the same sentence. See, throughout the class, throughout the lesson, this total concept is based on one single sentence. Again, at every question, I am repeating the same sentence because the total concept is based on this sentence only. What is that? Change in magnetic field or change in magnetic flux causing induced EMF or induced current in a circuit. Once again, change in magnetic field or change in magnetic flux causes to produce induced EMF or induced current in a circuit. That is called electromagnetic induction. Okay. Before entering into the topic, first of all, we must know the meaning of magnetic flux. Magnetic flux are a number of magnetic field lines which is passing through the given surface is called magnetic flux. Number of electric field lines which is passing through the surface is called electric flux. Similarly, the number of magnetic field lines which is passing through the surface is called magnetic flux. How can you find this value? See, here I am taking one substance. In that substance, this is area. A is the area. Now, for this area of the substance, I am drawing one normal. This normal I am taking as a unit vector. And the magnetic field lines, here it is passing. Here it is passing. Now, from this definition, the magnetic flux we can get pi is equal to B bar, A bar and cos theta. What is this theta? The theta is nothing but angle between magnetic field and unit vector. This is the theta. It is the angle between magnetic field and unit vector. This angle is cos theta. And finally, we can write phi is equal to b cos theta into a, or simply phi is equal to ba cos theta. This also we can write. And finally, the magnetic flux can be defined as it is the product of area of the substance and the component which is perpendicular to the plane of the surface. Perpendicular to the plane of the surface means this will be parallel component, this will be perpendicular component. Which is perpendicular component? B cos theta is the perpendicular component, and the product of area and component which is perpendicular to the plane of the surface, that is B cos theta, and this product gives the magnetic flux. What is its unit? Its SI unit is Weber. Its SI unit is Weber. Next, when the flux passing through the surface is maximum, when the flux passing through the surface is minimum. Suppose if theta is equal to 0 degrees, that is the unit vector and field both are parallel. In such a case, phi is equal to Ba cos 0 value 1, that is flux is equal to Ba. That means the maximum flux is passing through the surface. When it is maximum, the angle between the magnetic field and the unit vector, if the both are parallel, or if theta is parallel, means you will get maximum. Similarly, if theta is equal to 90, in such a case phi is equal to Ba cos 90. In such a case, you will get cos 90 value 0, then you will get the minimum flux. Minimum flux. Once again, if the magnetic field is parallel to the unit vector or perpendicular to the plane of the surface, the flux is maximum. Or the magnetic field is perpendicular to the unit vector or parallel to the plane of the surface, in such a condition, the flux is minimum. So once again, all of you try to understand the meaning of magnetic flux. What is the meaning of magnetic flux? The number of magnetic field lines passing through the given surface is called magnetic flux. What it gives? Phi is equal to Ba cos theta. Here I am taking one surface of area A. N is the unit vector and B is the magnetic field. And theta is the angle between magnetic field and unit vector. And finally, the magnetic flux is given by phi is equal to Ba cos theta. Its unit is Weber. When the flux is maximum, if theta is equal to 0, theta is equal to 0 means unit vector and field, the both are parallel. In such a condition, flux is maximum. If the unit vector and field is perpendicular, then flux is minimum. Now, we'll enter the exact topic, because this magnetic flux is useful for only one mark point of view. But now we'll exactly entering into the electromagnetic induction. Now I will perform 3 important experiments. Those are very easy experiments that everybody can learn by observing the board itself. You can learn the questions easily. That much easy questions. First, Faraday's experiments. Faraday's did some experiments on EMI. Now, all this one by one we will learn. See, first, coil magnet experiment. Coil experiment, and third one is also coil experiment. What is coil magnet experiment? What is coil magnet experiment? See, here I am taking one insulated coil. This coil is connected to galvanometer. This coil is connected to galvanometer. Now, this coil is insulated from each other and these two ends are connected to galvanometer. You already know, galvanometer is to detect the current. Now what I am doing, here I am taking one bar magnet. This is north and this is south. If I am taking one bar magnet, what's happening? Now here, see, initially, if the bar magnet, if the coil, if the both are not moving, if both are at rest, there is no current and the galvanometer shows null deflection. That means galvanometer shows zero deflection. If I am moving the bar magnet towards the coil like this, the galvanometer shows deflection one direction. If the same bar magnet, if I am moving away, again the galvanometer shows deflection in opposite direction. If I am keeping the bar magnet here, if I am moving the coil towards the bar magnet, again the coil shows deflection. If I am moving the coil away from the magnet, again the galvanometer shows deflection in opposite direction. And finally, we can conclude this experiment by learning one important point. What is that? If both are at rest, no current. If the one of the substances is moving, then you can see the deflection. Either bar magnet is moving towards or away, deflection is observed. If the coil is moving towards or away, deflection is observed. But if they are not moving, there is no deflection. Finally, from this experiment, it is concluded that whenever there is a relative motion between bar magnet and coil, the magnetic flux is changing. What is the magnetic flux? From the north, the maximum number of magnetic field lines are passing through this coil. If you are moving the coil towards, more number of magnetic field lines are passing through the coil. If the more number of magnetic field lines are passing, magnetic flux is changing, magnetic field is changing. Because of this magnetic flux is changing, and in that coil, induced EMF is produced. Induced EMF and induced currents are produced, and finally, because of this induced current, galvanometer is showing the deflection. And that is the main concept from this one. So once again, all of you try to understand whether the magnet is moving towards or whether the magnet is moving away. I already told you, this is the point. Again and again we have to repeat for continuously. Throughout the topic, this point only important. What is the point? If the magnet is moving towards or away, magnetic flux is changing, magnetic field is changing, and that creates induced EMF in the coil, and induced currents is produced in the coil, and that is measured by using galvanometer. Again, either it's the same way the coil is moving towards the bar magnet, or if the coil is moving away from the bar magnet, again flux is changing and induced EMF is produced, and finally that induced current you can measure by using galvanometer. So this is all about coil magnet experiment. Next, coil experiment. Coil experiment. See, once again I am taking one insulated coil which is connected to a galvanometer. Next, here one more coil I am taking that is connected to a battery, but their axis is same, common axis. What changes I have made from this one and previous experiment? In the previous experiment, this coil is named C1, this coil I named C2. In place of C2, I kept one bar magnet. But here, C1 just similar to the previous one, coil which is connected to galvanometer. C2 again one more coil, but it is connected to a battery. But previous one here bar magnet is there, but now here it is a coil with a fixed DC battery is connected. Now what is happening? If C1 coil, if the C2 coil, if the both are at rest, there is no deflection is observed in the galvanometer. Now here, coil C2, if I am moving towards the C1 or if it is moving away from the C1, there is a deflection is observed. If it is moving towards one direction, if it is moving away another direction, the galvanometer is showing the deflection. Similarly, if C2 is kept constant, the C1 is moving towards the coil, one direction deflection is observed. If the C1 is moving away from the coil in another direction, deflection is observed. And finally, from this one also it is concluded that there must be a relative motion is there between coils C1 and C2. If there is no relative motion, there is no induced EMF, there is no induced current. So definitely a relative motion must be there. What is that one? Either you have to move C1 or C2. Otherwise, if the both are at rest, there is no deflection which is observed in the galvanometer. So finally, from this one, it is concluded that one more important point, the same point. What is that one? If you are one of the coils, if it is moving towards either moving towards other coil or moving away from the other coil, what is the point? Magnetic flux changes, magnetic field changes, and this is causing to produce induced EMF in the nearby coil, and finally induced currents are produced. So this we call it as a coil experiment. Next, coil experiment. See, once again I am taking the coil which is connected to galvanometer, and next one more coil I am taking. This is connected to battery with pressing key. Pressing key. This is the battery. This is the key. Now, here and here only one difference is there. Here there is no key. Here I am using press key. Then what is happening? See here. If I am pressing the key, just like an on-off switch. If I am pressing the key, circuit is closed, current is passing, current is increasing, and flux is changing, and the momentary deflection is observed. It's just a fraction of seconds, it shows the deflection. Once the key is completely closed, there is no increase of current. In such a case, there is no change of magnetic flux. There is no induced EMF, no deflection. In the same way, next, if I am opening the key, the current starts decreasing, flux changes, induced EMF is produced in the galvanometer, momentary deflection is observed. If it is completely open, there is no change in flux, there is no induced EMF is produced in the galvanometer. So finally, here, what is the importance? Here, only momentary deflection is observed in the galvanometer while you are pressing the key, while you are opening the key. That time only momentary deflection is observed in the galvanometer. Why? Because if it is closing, that fraction of seconds time only flux is changing, EMF is producing. While you are opening, that fraction of seconds time only, again the momentary deflection is observed in the galvanometer. So from this one, from these three experiments, it is concluded that the magnetic flux is changing, induced EMF is produced in the coil. Induced EMF is produced in the coil. And next, Faraday's laws of electromagnetic induction. Highly important question, 2 marks, highly important question, and very easy question. What we have learned from this experiment, that is the laws. What is the laws? Whenever there is a change in magnetic flux, induced EMF is produced in the circuit. That EMF lasts as long as magnetic flux changes continuous. That is the first law. What is the second law? The magnitude of induced EMF is directly proportional to rate of change of magnetic flux. Already told you the first law. What is the first law? Whenever there is a change in magnetic flux linked to the circuit, EMF is produced. That will last for as long as magnetic flux changes continuous. What is the second law? The magnitude of induced EMF is, suppose if I am taking at a time t1 flux is phi1, at a time t2 flux is phi2, and finally we can get this one phi2 minus phi1 by t2 minus t1, or E is equal to change in flux. I can take it as a pi, time I can take it as a t. So E is equal to d pi by dt, or here I have to keep one more symbol minus. So E is equal to minus d pi by dt. E is equal to minus d pi by dt. What it indicates? The magnitude of induced EMF is directly proportional to rate of change of magnetic flux. And here the negative sign indicates the induced EMF is try to oppose the change in magnetic flux that is produced in the circuit, and this can be, we can find by using one more law. That law is called Lenz law. By using that law, we can know why you got this minus sign and everything. So once again, all of you must recollect those 2 points. What are the 2 points? Faraday's laws. Magnetic flux changes, induced EMF is produced. What is the second law? The magnitude of induced EMF is directly proportional to rate of change of magnetic flux linked with the circuit. And here the negative sign indicates that the induced EMF is trying to oppose the change in magnetic flux that is produced in the circuit. So this is the first class. Everybody must learn this one.